This conference will now be recorded.
So good evening. We were learning what is polarization, and we had seen that polarization can be observed in case of transverse wave, and light is a transverse wave, so we see polarization in case of light, okay, or electromagnetic wave. So we have seen what is called polarized light, what is unpolarized light, and if you remember, we had used a notation like this for unpolarized light. Okay, so where the double arrow, only this part, this represents the electric vibration in the plane of the paper, and if you see somewhere only this dot, this actually represents electric vibration electric vibration perpendicular to the plane of the paper. So these are the things we have discussed, and we have discussed what is polarizer and analyzer. I'll just briefly tell you what is called polarizer and analyzer. Suppose you have a light, okay, you have been given a light from some source. You have to examine whether the light is polarized or unpolarized. So we have seen, if you have unpolarized, okay, let me give you another way of representation of unpolarized light, so which has vibrations along all directions in plane. Okay, so if you have, and we have seen that polarizer can be of different shape, and polarizers generally like in market, polarizers are available, they are used in camera, etc. So these are thin sheets which can absorb some, like, some vibrations of the unpolarized light, and the other will be passing through. So look, we have seen, if the polarizer, this is, suppose polarizer has the axis, so this is called optic axis of the polarizer, optic axis of polarizer polarizer. So what it does, as the unpolarized light, so this is unpolarized light because it has vibrations, electric vibrations in all directions. So this is unpolarized light. So once it passes through this, you will have only vibrations which are parallel to the optic axis. Okay. Now if you keep another identical polarizer which has optic axis parallel to the same, you look here, if suppose the intensity is I 0, see half of the vibrations are cut off, right? So half of the vibrations, like, see, you may think of vibration like, see, in plane and out of plane, perpendicular. So these constitute the whole unpolarized light. So when passes through the polarizer, one set of vibrations will be absorbed and another set will pass through. So the intensity will be naturally I0 by 2. Okay, the half of the intensity of the unpolarized light. So this is actually called plane polarized light, since the vibration is actually confined in a plane. So if you take this analyzer, so this polarizer, another identical polarizer, okay, having the optic axis, having optic axis parallel to the previous one, okay, then see the intensity does not change here. This also will pass like this, okay. So same intensity will pass from here. Now if suppose this second analyzer is kept at certain angle with the previous one. Suppose the optic axis of the previous one, sorry, optic axis of this is making certain angle like this. See, earlier it was this, now it is certain angle. It is making certain angle. Then the intensity will not be the same as here it is. So it will be actually given by Mallo's law that we have already discussed. Okay, this was just a recap. And this guy, see, you look, if you rotate, if you have the same, see, these polarizers P1 and P2, these are called actually polarizer if you use them individually. But when you take the two, and if you just take P2 and rotate this P2 at different angles, then the intensity will not be uniform. Somewhere it will be 0, like there will be two places where it will be 0, and two places there will be maximum, and in between there will be the intensity less than the maximum. Okay. So this polarizer is called the second polarizer, which is actually helping you to, so when, yeah, helping you to understand whether the light passing through this is an unpolarized light or polarized light. That's why it is called analyzer. The second polarizer is called the analyzer. Okay. All right. So this is what we have learned. Now what we'll do, we will see method of polarizations. Naturally there are few methods, and there are some some methods which actually are artificial. Artificially also light can be polarized. So there are basically four ways of, like, four methods of polarizing light into a plane polarized light. So these are two: scattering and reflection. These are natural way. And say double refraction and selective absorption, these are also, obviously all are natural process, but this can be actually done uh, by using double prism, double refraction by nickel prism. Nickel prism is actually made specially for polarizing light into like unpolarized light to polarized in plane polarized light. And selective absorption. So basically these two first two are discussed in your book, so we'll be discussing here, and rest you will learn in your higher classes. So we'll see how by scattering light can be polarized. Okay, so look, when you see we see sky as blue. Actually, if you see a clear sky, that will be bluish in color, and we have learnt actually. So blue color is due to blue color of sky is due to scattering of light. Okay, that we have already learnt in previous chapter in the geometrical optics chapter. Okay, this blue color of sky is due to scattering of light. Scattering of light, and actually scattering, the degree of scattering depends, like it depends, or it varies, you can say it varies inversely proportional to 1 over lambda to the power 4. Okay, intensity, scattered intensity. So it depends like this. Okay, so in case of blue light in the visible range has the least uh yeah, so blue light has the least wavelength. You might be thinking, what about violet? Violet is actually not seen very properly, so that's why blue light has lesser wavelength, so the scattering will be very, like it will be more, scattering will be more. So that's why we see clear sky as blue in color. Now if we look the blue portion of the sky through a polaroid, in the sense, if I just say through the polarizer, maybe not polaroid, let us say polarizer, and if you just rotate the polarizer, then what you see the intensity variation of the light. So as I was telling you in the just before, few minutes before, so if you have a polarized light, suppose I have polarized light, and if I pass through this analyzer, you just rotate the analyzer, then you see at this position you will see intensity of the light. Okay, there will be no change. As you see here, if it is I 0 by 2, here it will be I 0 by 2. But once you rotate the optic axis here, intensity will fall, and sometime it will be see 90 degree at this angle, the intensity will be 0, and again it will be increasing, and this side again when it is rotated, it will be again 0. So you can see there will be intensity variation. Okay, intensity variation. So somewhere it will be so bright, sometime it will be so bright, sometime it will be little dark. So this is happening due to the polarization. Okay, this is due to polarization. As you look here in this figure, see, suppose the sunlight is coming to our atmosphere as an unpolarized light. Actually, any source you take, any natural source, the light coming out from any natural source is unpolarized in nature. So sunlight also is unpolarized. But when it enters into the Earth environment, so what happened? There we have air molecules, dust particles, etc. So when the sunlight is actually falling on some molecules, okay, some molecules, what happens? You have in molecules you have electrons, okay, and electrons are charged particle, right? Electrons are charged particle, and electric field. See, this light is actually represented by electric field and oscillating electric field. Okay, oscillating electric field like that. So it is electric field. When it actually encounters an atom, what happens? Atom has electrons, right? Atoms has electrons in it. So electrons are charged particles. They will be actually influenced by electric field because it will give some force to that those particles into. So for some force, electric field will apply force on this electrons on the molecules or the atoms. Okay. So those electrons will start oscillating. What it will do? It will start oscillating. But this oscillation, the oscillation can be of two types. Since this light is unpolarized, the electron can oscillate in two ways. Okay, it can oscillate in plane. Okay, in plane, and it can oscillate out of plane also, or perpendicular to the plane. In both way, it will oscillate. See now, if you see this is an observer we have kept at right angles to the sunlight. The sunlight is coming from this, so this is 90 degree at right angle. We are just keeping some observer. Okay, so what it will do, this molecule, in fact the electrons, see they oscillate, starts oscillating with the electric field, and as you know, oscillating charged particle will radiate electromagnetic wave, or they will radiate light, right? Or electromagnetic wave of same frequency as the electric field, right? So these electrons oscillating oscillating electrons will radiate light. Okay, radiate light. But the vibration, see, you have all types of vibration. You have in plane vibration, you have electric field out of plane. Okay, or 90 degree, like 90 degree or perpendicular to the plane. Now if you keep some observer perpendicular to this incoming ray, what you see, you will see one particular vibration. Okay, one particular vibration you will see, because in this particular direction, electron is oscillating perpendicular to the plane of the paper. So in this direction, electron has oscillations. Electron oscillates oscillates perpendicular to the plane. That's why, and actually, in which direction it oscillates, it will actually radiate electromagnetic wave in that direction itself. Okay, plane of paper. Okay, so that's why in this direction you will see only one type of vibration, that is perpendicular to the plane of the paper, because electron oscillates in this direction, in like out of plane of the paper or perpendicular to the plane of the paper. In some other direction you may get the other vibration. Okay, so this is how, upon scattering, this phenomena is called scattering. So what happens in scattering when electromagnetic wave, so this is like light is electromagnetic wave is, and light is always characterized by electric vector. When electric vector is encountering an atom or molecule, it has electron within it. So those electrons will oscillate with the electric field with the same frequency, etc. And when the electron is a charged particle oscillating, it will radiate light or electromagnetic wave. So the frequency of the radiated light will be the same as the electric field, because the electric field induces oscillations to the electron. So this frequency of the oscillations of the electron also will be the same as the electric field. So it will radiate light of same frequency. But see, unpolarized light had two different vibrations. Okay, one is this direction, suppose, and another one is in this direction. Okay, so electron also will vibrate in two different directions, and some electromagnetic wave will be like this way, and some electric field will be in this way. And if the observer, some observer is here, he will see some, like, only one type of vibrations, and in this the observer will see another type of vibration. Okay, so these are actually polarized in nature. These are plain polarized light. Okay, this is how by scattering you can get polarized light. Okay, so famous Indian scientist C.V. Raman had done various experiments on this scattering of light, and because of his because of his famous experiment Raman effect, he had been he had been awarded Nobel Prize. Okay, now we'll go to the next part. Okay, so here I was trying to uh, give you the feeling of how you can analyze a light, whether it is polarized or unpolarized. So this is what I have already discussed in the beginning, so I'm not repeating this. So yeah, now we'll see method of polarization of light by reflection. So by reflection, how we can polarize a light. So you can understand whatever light we see, like which are coming from some, like coming whatever reflected light we see. In fact, I can say whatever reflected light you see, actually those are polarized, partially or fully, completely polarized light. So see, reflection by sorry polarization by reflection, this was experimentally studied by French scientist Molas. Okay, in 1808, French scientist Malus had studied this experiments. So what he had seen, if you pass an incident unpolarized light through, like, if unpolarized light encounters a excuse me, encounters a transparent medium. Suppose this is air, or as it is written here, medium of some refractive index mu. Let us take that. And when the light is incident on the surface of transparent medium, the reflected light is partially plane polarized light. So reflected light is partially plane polarized light. So this is what was the observation by scientist Malus. Okay, and what he said. So what was the observation? When a light is light incident on a transparent medium, the reflected light is partially polarized. Partially polarized. Okay, and this degree of polarization or the extent of polarization will depend on the angle of incidence. So another observation he made was the extent of polarization depends on the angle of incidence. Okay, angle of incidence. The reflected light is found to be completely polarized, and the reflected light was found to be completely polarized light. Okay, so the reflected light was found to be completely polarized when the reflected and refracted light are perpendicular to each other. Perpendicular to each other. I'll explain you in this figure. Okay, look, what does this mean? So we have seen uh, physicist Malus had already observed that if a light incident on a transparent medium, suppose this medium has refractive index mu, then some part of light will be refracted, that we know, and some part will be reflected. So the reflected light was partially polarized, but there is a particular situation when this this is reflected ray and this is refracted ray, they make an angle 90 degree. At that situation, the reflected ray, as you see from here, reflected ray will be completely polarized. Okay, completely polarized means you have only one type of vibration. So this see, so the reflected light will be completely polarized with the electric vibration perpendicular to the plane of the paper. Okay, so and the refracted ray will be actually unpolarized, that will remain unpolarized. As you see, there are both the vibrations here in the refracted ray. Okay, but this does not happen every time, or so that means what? See, light cannot be completely polarized unless this angle of incidence, the reflected ray and refracted ray, they make an angle 90 degree. This is the condition when the reflected ray will be completely polarized, and this does not happen for any angle of incidence. Okay, it depends on angle of incidence. If the angle of incidence is this particular angle of incidence, there will be a particular angle of incidence for which the reflected ray and refracted ray, they will be perpendicular to each other, and that depends on the refractive index of the second medium. Okay, I'll repeat this. See, the reflected ray will be completely polarized if the reflected ray and refracted ray, they are perpendicular to each other. They makes 90 degree angle in them. But this does not happen with any arbitrary angle of incidence. It depends on angle of incidence. So it happens for a particular angle of incidence for a particular set of material. Suppose air and this is water, there will be a particular angle of incidence. If it is air and glass, there will be a particular angle of incidence for which this these two rays will be perpendicular to each other. So this particular angle of incidence is called Brewster's angle. Let us write the definition. So the angle of incidence at which the angle of incidence for which the reflected ray and refracted ray become perpendicular to each other. Perpendicular to each other. Perpendicular to each other. Okay. So that particular angle is called angle is called that particular angle of incidence. Angle of incidence is called Brewster's angle. Brewster's Brewster's angle. Okay. Or sometime this Brewster angle is termed as Brewster's angle, also termed as angle of polarization. Angle of polarization. Angle of polarization. Angle of polarization. Okay. So the British physicist David Brewster found this relationship actually. He had discovered this, that at particular angle of incidence this happens for a set of medium. Okay. And that's why this angle is called Brewster's angle after the name of David Brewster, the British physicist. Okay. And we'll see there is a nice law given by Brewster. We'll try to find out what is the Brewster's law. Okay, you have been saying this Brewster's law. Okay, look, if I say there is a particular angle of incidence which is denoted by theta b, Brewster's angle. Theta for angle of incidence and b for Brewster's angle. And at this situation, the angle between this reflected ray and refracted ray is 90 degree. And as we know, because of reflection, this also will be theta b. Okay, and let us suppose this is r, simply refracted, like angle of refraction, this is r. If this is 90 degree, so you know this line will be having total of 180 degree angle. So from this figure what we can say, see, if this is 90 degree, then we can say theta b plus r also will be 90 degree. Okay, because this whole angle has to be 180 degree. Look here, theta b plus 90 plus r, that whole angle has to be 90 degree. Sorry, 180 degree. Okay, I'll just elaborate it. So theta b plus 90 degree plus r has to be 180 degree total. Then what is this? Theta b plus r is 90 degree. This is what we are writing directly here. So from here we can get, so I'll just clean this part. So we can find out what is r. R is 90 minus theta b. Okay, we'll keep it there. Now see, From Snell's law, what we know? Suppose this medium has refractive index mu. From Snell's law, what we can write? We can write 1 sine. This is a 1 means refractive index of the air sine theta b. This is equal to mu into sine r. Okay, or mu is equal to sine theta b by sine r. Okay, from for this interface. Okay, for this interface I am writing. So look, I have already got a relation between this thing. Okay, sine not b, sine theta b, sine theta b and r. This is sine theta b. So sine theta b as it is, let us keep, and see this is sine r. Sine r means 90 degree minus theta b. Okay, and this can be written as, from trigonometry we can write this as sine theta divided by, this is cos of theta. So theta b, and this is cos of theta b. Okay, 90 minus theta b is cos theta b. So what does it give you? So this gives you, see look, I'll write it here. So mu is equal to tan theta b. So where, so the refractive index, so you can see there is a relation between refractive index and the Brewster's angle. Okay, Brewster's angle. So this is why the see the reflected ray and refracted ray, they cannot be perpendicular to each other for any arbitrary angle of incidence, because it depends on the mu. Mu is the refractive index of the second medium, and for a particular medium there will be particular set of medium, there will be a particular angle of incidence, and that can be obtained from this law. This is actually, this equation is known as Brewster's law. So I'll just repeat the derivation once again. See, we have taken theta b as that particular angle of incidence for which these two guys will be perpendicular to each other, this reflected ray and refracted ray. So from the geometry I can say that theta b plus 90 degree plus r, this has to be total 180 degree, and from there we can find out what is theta b plus r, that is 90 degree, and from there I can find out the angle of refraction. And now from Snell's law, what you know, Snell's law, n1 sine theta 1, okay, or ni sine n1 sine theta I plus n2 sine theta r, r for refracted. Okay, refracted angle of refraction, this one. So from there and using this, what we got mu is equal to tan theta b if this angle of incidence is theta b. Okay, so this is called angle of polarization, this theta b, this is called angle of polarization or Brewster's angle, and this particular equation is known as Brewster's law. Okay, this particular equation is known as Brewster's law, and from here there will be numerical problem. Okay, there will be numerical problem from this particular portion. Okay, this particular, so in whole polarization part, this is the only equation or derivation you have, and from here you will be able to solve numerical problem. Okay, so there are two problems I have just, see, the problems will be always related to Brewster's angle and Brewster's law, and maybe the language of asking you the problem will be different. Like I have taken two of them. See, I have taken a set of problem, like a pair of problems. See, this problem is asking you a ray of light strikes the glass plate. So you have a glass plate. It strikes the glass plate. Suppose this is the normal at an angle 60 degree. At an angle 60 degree, 60 degree. If the refracted and refracted rays are perpendicular to each other, find the refractive index of the glass. So, so this is nothing but Brewster's law. Brewster's law we can find out from Brewster's law. Okay. So this is the condition here. This is 90 degree. Okay. So you have to find out. So see, mu means tan theta b. So if you know this Brewster's law, then it is very easy to find out. Okay. So what is refractive index? Tan 60 degree. Okay. 60 degree. You have to somehow understand this angle 60 degree, whether it is Brewster's angle or not. Then only you can apply this formula. So from here you can get 1 by root over 3. Okay. Tan 60 degree 1 by root 3. Okay. So from here you can find out the value. Okay. If you don't want to find, you can keep like this also. Okay. If you are given particular options, then you can use this root over 3 means 1.732. Okay. At least 1.73 you can use, and then you can divide 1 with that, and then you can find out the particular value of the refractive index. Okay. So this is how problem like this is one way of asking problem. And see, another way of asking problem is, if the velocity of the light in water is this much, then what is the angle of polarization? You will be asked like this also. So how to do that? See, you have to find out. See, you have to find out the refractive index of the water. Then angle of polarization you can find out. Okay. So that means what? You have to find out what is mu. Mu is c by v, speed of light in air. So that is 3 into 10 to the power 8 meter per second. And v, the speed of light in the medium. Here the medium is water, and the speed of the light is given as this, 8 meter per second. Look, this will be 30 by 22. So 15 by 11. Okay. So this will be 1 point. So you can just divide this 4, so this 3, 7. So it will be something like 6, 1.36, something like that. Okay, 36, 3, something like that. Okay, so this will be the value if you go up to second decimal. So this is the refractive index. Okay, so this is how numerical problems will be asked in exam from this part. Okay, so thus we have completed this chapter. Now we'll start, not now, not today. We'll ask, hereafter we'll go for the next chapter, that is dual nature of radiation and matter. So first we'll be learning photoelectric effect, then de Broglie's hypothesis, etc. Okay, so that will start in the next class on Sunday. Today actually I have completed this chapter, and I would like to stop it here for today. Next class we'll be meeting on Sunday. Okay, so bye for today. I'll stop it here.